So hello students, in this class we will discuss about the azepines. Now it is an example, or azepines are the example of one of the important heterocyclic compound. Now the name is azepines, as you can see it is written over here, and the simple structure of azepine is. Now the difference between the other heterocyclic compounds and azepine is azepine is a 7-membered ring. As you can see, seven members are there in this whole ring structure. Among them nitrogen is number one, and other 6 atoms are the carbon atom present in the structure. Now we will go to a brief introduction about the azepines. Now you can see azepines are unsaturated heterocyclic compounds of 7 atoms with a nitrogen replacing a carbon at one position. Now these are the different conformation. As you know, all the heterocyclic compounds have the different conformations. In case of azepines, they have the both conformations. Now azepines and its tautomers exist in non-polar conformation, that is both conformation, and the structure of the both conformation is mentioned over here. Now azepines do not comply with Huckel's rules of aromaticity actually. So azepine is a non-aromatic compound. Other heterocyclic compounds just like pyrrole, furan and other compounds are aromatic, but azepines are non-aromatic compound. Now what are the importance of azepine rings? Now first of all, if the medicine we can follow the medicinal use, that is your anticonvulsants. Now and among the anticonvulsants, the examples of azepine derivatives, the first one is carbamazepine, and second one is oxacarbazepine. Oxacarbazepine and carbamazepine are important drugs. They are used as anticonvulsant drugs, and this is the simple structure of carbamazepine, and it actually contains 3 ring structures. Among them, 2 are the phenyl rings, and another ring present in this structure is azepine ring. As you can see, azepine ring along with it CONH2 substitution at the position 1 of the azepine ring present in this structure, that is the carboxamide group present in this structure. Now the second importance, the azepine ring also present in different tricyclic antidepressants. The compounds are tricyclic antidepressants. Now example of common tricyclic antidepressants are imipramine, desipramine, clomipramine. All are the examples of tricyclic antidepressants, and here the simple structure of tricyclic antidepressant of example imipramine is represented here. Here the 3 rings also present for this compound also, that is 2 benzene ring along with azepine rings, but all azepine ring contain a specific substituent at n position, that is dimethyl amino along with a propylene bridge. Along dimethyl amino group is there along with a, this is your propyl bridge. Now we will see about the different chemical properties as well as the structures and the synthesis by different methods of azepine ring. Now here we will discuss about the tautomerism of azepines. As you can see, there are 4 structures are represented here, that is among them the first one is your 1H azepine, and the second one is 3H azepine. The position of the double bond is shifted, and this carbon present in this structure, it contains 2 hydrogen. And the third one present here, that is 4H azepine. The positions of the bond is also different. For this double bond present in this structure is actually different for 4H azepine. Now go to the fourth one. This is your 2H azepine. Here the double bond is again changed, and the carbon atom present adjacent to the nitrogen atom, it contains the CH2 group. Now this is all about these are the four tautomers present in the structure. These four tautomers can be possible for the derivatives of azepine as well as unsubstituted azepine. So nitrogen 1H azepines without a substituent on the nitrogen atom are rare. They are tautomerized to 3H isomer. So without any substituent at one N position, that is in one position, is actually finally tautomerized to 3H isomer, and this is actually an unstable structure. That means this 1H isomer is an unstable structure and it is converted into 3H isomers. Now stability of 1H azepines is enhanced by electron withdrawing substituents, especially at position 1. So if you place electron withdrawing substituent at position 1, then the stability of this compound will be increased. So this is the synthesis of azepines. Now, so the first reagent used for valence bond isomerization, the title of the experiment is valence bond isomerization. By using the first reagent used is benzene, and second reagent used for this reaction, that is ethyl carbon acetate. The ethyl carbon acetate, this is the specific structure of ethyl carbon acetate. Now whenever these two compounds react in the presence of H nu, that is your light, and in the presence of nitrogen, that is minus N2, they actually converted into this specific complex structure. As you can see, the double bond present of the benzene ring here, it is finally broken, and among them two nitrogen actually forms two nitrogen form the new bond with the nitrogen atom along with the specific substitutions. So whenever there are some modifications of the bond, that is this bond is shifted here, and there is also bond shifted bond, and finally the double bond shifted into this one. So then finally we get this 7-member structure of azepine, obviously with a specific substituent present here. Now this is the specific structure we get after the modification of the double bonds in the structure, obviously along with a specific substituent. Now whenever on heating in the presence of OH minus ion, this specific substituent present in the structure, this is the specific substituent, is actually eliminated from this ring, and finally we get the 1H azepines by this reaction, and the reaction is very common, that is valence bond isomerization reaction. Now what are the steps involved in this reaction? That is the steps involved for this reaction, that is first one is bond recognition, second one is recognition of alpha and pi electron without rearrangement of the atom. So if there is an example of without rearrangement of the atoms, you can say you can write down the examples of these valent bonds isomerization. In this whole reaction we can just see there is bond reorganization, and reorganization of the pi electron is there. As you can see in the structure, only the reorganization of the bond is there without any rearrangement of the atom. Always remember, this synthesis of azepine is always without any rearrangement of the atoms. So as you can see, this is the another reaction of azepines derivatives. Now the reagent used for this reaction is from phenylazide. Now this is the specific structure of phenylazide. Phenyl ring along with 3 nitrogen is present in this reaction, that is your phenylazide. Now on heating, elimination of nitrogen gas, that is minus N2, this specific structure of phenylazide is converted into benzazirine. This is the structure of benzazirine. The first step is from phenylazide, we get benzazirine. Now again I can repeat, that is from whenever we take phenylazide in the presence of or in on heating, the nitrogen is eliminated from the structure, and finally we get benzazirine. You can see the structure, the specific structure is there. The bond present in this position, double bond, is actually broken and a specific nitrogen is attached into the whole ring system. Now next stage is there, next step of this reaction is there, that is whenever benzazirine is react with this specific reagent, name the reagent, very simple name, that is diethylamine. So diethylamine is there. Now whenever benzazirine react with diethylamine, they actually converted into this specific structure. Now the name of this structure is 1H azepine. Obviously the structure represents the 1H azepine, and obviously it is a derivative because the two position, now this is your position 2, is contain a specific structure, that is diethylamine moiety is there. It contains at position 2 the specific diethylamine moiety is there. Now that is why it is termed as azepine derivative. Now this is the last step of this reaction, that is whenever diazepine derivative finally go for the isomerization reaction, this is your isomerization reaction, and they form the diethylamino 3H azepine. Diethylamino group present at two position, as you can see. Whenever we at first whenever we discuss about the structures of azepines, the numbering will start from this is your number 1, and this is your number 2, and this is your number 3. So that is why the substituent present at position 2, diethylamine. So that is why the compound is 2-diethylamino 3H azepine. The structure of the azepine represents the 3H. Now this one is your 1H azepine, that means this is the 1H tautomer, and the second is your 3H tautomer. Now this is all about the synthesis of azepines from phenylazide. From phenylazide, the synthesis of azepine is discussed. Now on heating, at first we get benzaziridine. After that, in the presence of diethylamine, we get the 1H azepine derivative, and finally whenever isomerization reaction is there, we get the 2-diethylamino 3H azepine. Now again, this is the third reaction by which we get the azepine derivatives. Now the reagents, at first we have to know about the reagents. The reagent used for this synthesis is your C6H5NO2. Now what is the name? of this reagent, that is nitrobenzene, C6H5NO2 nitrobenzene. Whenever a specific reagent is there, name is mentioned, that is tributyl phosphine. Tributyl phosphine, this is the specific structure of tributyl phosphine. Whenever nitrobenzene reacts with tributyl phosphine, actually you get a specific structure, that is deoxygenation of the nitrobenzene, and only nitrogen is there along with its lone pair along with the benzene moiety. That is your deoxygenation reaction is there. This is elimination of the nitro oxygen atom from this structure. Now this is the first step, and the next step, whenever these deoxygenated nitrobenzene react with OH group along with any R, that is your alkyl group present in the structure, actually there is a rearrangement of the ring system. As you can see, the OR moiety is attached at the specific position, and the double bond present in this structure is actually opened, and one of this carbon is attached with nitrogen and another bond is with OR. Now there is also a changes or rearrangement of the bonds. This double bond is shifted here, and the double bond present, it is actually shifted in this position. That is why rearrangement of the bond again is there. Now finally, whenever bonds are rearranged, we get this specific structure of azepine derivative, obviously with a substituent at two position, that is your OR. Now the reaction is for the general substituents. R represents any of the alkyl group present in the structure. Now in the presence of hydrogen atom, you can see in the presence of H plus ion, sorry, not atom, H plus ion, it is finally converted into this specific structure of 2-alkoxy-3H azepine. 2-alkoxy-3H azepine. Now if we want to discuss about at a glance this reaction, what are the steps? So deoxygenation in the first reaction, that is your deoxygenation of NO2 group by the help of tributyl phosphine reagent, by the help of tributyl phosphine reagent. The second stage, nucleophilic addition of alkoxy group, nucleophilic addition of alkoxy group by aryl nitrine, nucleophilic addition of alkoxy group, and finally the final stage we get whenever we get the azepine, that is the rearrangement of the bonds present in the structure. So this is the synthesis of azepine derivatives from nitrogen, from nitrobenzene. That is, at first nitrobenzene is deoxygenated by the help of tributyl phosphine. In the second step, whenever we get the deoxygenated nitrobenzene in the presence of ROH, it is converted into, or the some substitution of the alkoxy group in the structure. This is the alkoxy group present in the structure, and finally rearrangement of the bonds actually produce the specific structure of azepines. Now these are the properties of azepine derivatives. The first reaction, that is your thermal reaction. Now whenever you can see, this is not actually azepine, there is a specific derivative of azepine, that is in carboethoxy 1H azepine. It also represents the 1H tautomer. In carboethoxy 1H azepine, the group present, that is your carboethoxy azepine, whenever it is heated up to 200 degrees Celsius, the temperature is 200 degrees Celsius, on heating it is actually converted into N-phenyl carbamate. It is converted into specific structure N-phenyl carbamate. Now the 7-membered ring is actually converted into a 6-membered ring. You can see methyl group is as it is, but the 7-membered ring is converted into a 6-membered simple phenyl ring. Now go for the next reaction, that is ring contraction. The reaction is ring contraction. Now the same reagent, same compound is taken here, that is N carboethoxy 1H azepine 2 methyl N carboethoxy 1H azepine, because the methyl group present at 2 position and the carboethoxy group present at position 1. That is why the compound is 2-methyl N carboethoxy azepine. Now whenever this compound in react with methanol, obviously in the presence of light, that is H nu, it is actually converted into this fused ring structure. One of them is four-membered and another one is your 5-membered simple pyrrole ring, obviously with methyl substituent present at 2 position and ethyl carboxy group present at 3 position. Now the third reaction for azepine derivatives, that is Diels-Alder reaction. Now this is the specific structure of azepine derivatives, that is ethyl carboxy group at position N. Now whenever it reacts with this 5-membered compound, actually it is a huge structure with two phenyl substituent present at adjacent position and methyl carboxy group present at the two adjacent position, and as well as a carbonyl group is there. Now whenever these two compound react with reacts in the presence of the reagent used for this reaction, that is your benzene, at 800 degrees Celsius, a specific huge structure is formed. Actually a fused ring formation is there. The 5-membered ring which is from the which react with the azepine derivative, it is as it is, and the whole azepine ring is attached over here, but a simple modification along with the specific groups or substituents present here. This is the Diels-Alder reaction for azepines.